Hello. In this video, I would like to show DMI in combination with SPI protocol, and that for a STM32. And have a very extended example of how you can use this. Further, in this video, I'll shortly explain about how the serial peripheral interface protocol works. So we have a short introduction on SPI. We will apply it for a LCD screen, the Nokia 5110 screen, and that's driven by the PCD8544 chips. So we'll also look a little bit into the operation of this chip, so that we also can understand how the software works and how the protocol is applied for this specific chip. Then I'll talk a bit about the software paradigm. So let's say the software benefits and the software point of view, and why this use of DMA, especially in this example, is beneficial. Then we go to the more practical stuff. So setting up CubeMX with the example, and also with the software, and then we'll discuss a simple library, walk through the code so that you understand what is happening, and then can use the library as is, or just extend the library with your own wishes. Okay, so first let's talk about the SPI protocol. The SPI protocol is a very simple protocol. You have a master and a slave, and master means that the master initiates the transfer of data, and the slave accepts the data. The slave also cannot throttle any data or something like that, so it really has to accept the data that is given by the master, and that makes it quite simple protocol. So let's look into the pins. You have basically 4 pins in the protocol. We'll discuss only 3 of them because we will only want to transfer information from the master to the slave and not vice versa. So the first pin here shown is called MOSI, and it stands for master out, slave in. So that's why it's an output of the master. We also have the pin master in, slave out. That's the data transferred from slave to master. We will not discuss that in this video. Then you have a clock signal, and you have a ship select signal or a slave select signal. If you look into more detail in the protocol, then it looks like this. First, what happens is that the master initiates the transfer by pulling the slave select low. It's a low active signal, and at that moment, the master can generate a clock, as you see in the top signal here. And at the same time, the master or the controller also generates a data pattern. And the only thing the slave does is basically clock in the data that the master provides. With respect to the signal levels of the clock, and also the moment at which the data is clocked in by the slave, there are several possibilities. You can start off with a low clock or start off with a high clock. This is typically called clock polarity in the protocol. That can be 0 or 1. 0 is for a low clock. So at this specific example, we have clock polarity is 0. And the second thing you can, let's say, decide on is whether you clock in the data at the first edge or at the second edge. In this case, it's the rising edge or the falling edge. If you look at this specific example, you see that each time you have a rising edge of the clock, the data is stable. So and that means also that for the clock phase, as it's called, we have what they call 0. That means basically the first edge, or in this case the rising edge, is the edge that has to be used to clock in the data, and basically that's it. It's a very simple protocol. So now let's look a little bit into the LCD display. As said, it is driven by the Philips PCD8544 chip. And to be honest, I really like this chip. It is really very simple design. It's very straightforward, no bells and whistles. So from a hardware perspective and also from conceptual perspective, it's really very simple. The data sheet is very clear. The display itself is a small display, and of course there are lots of small displays, but this is one of the few displays that really has in sunlight very high contrast, because it's a reflective LCD. Of course you have very small OLED displays, but if you have a OLED display, small OLED display in full sun, you have very poor contrast. And also what is nice, it's very low priced, and I think it's on AliExpress you will find it for €4 or even less. For STM32 is also very nice that it has 3V 3 signaling, because at the time of design it already was designed as a low power chip for a cell phone. So you don't need any level converters to interface with the STM32. The display itself is a purely graphic display, so it has no character sets or whatever. So everything that you do with text needs to be done by the controller. The SPI clock speed can be up to 4 megabits, which is quite fast at that time, because I think it's a display that was designed in the early 90s. So if you look at the number of pins that you typically find on such a display, you will find 8 pins. You have the SPI pins, that accounts for 3 pins. That is the clock, the data, and the chip select. Then of course you have the power supply, so VDD and ground. But you will still have some additional pins. They are specific for this chip, and that is the DC pin, and that says basically whether what you send to the chip is data or a command. The other pin is a specific reset pin to reset the chip, and optionally you can also have a backlight on most modules. So inside the chip you have a 504 byte RAM, which contains a frame buffer, and it has an auto increment, and that means that you can basically specify a pointer in the frame buffer, and if you then write data to it, the data will land at that specific address of the frame buffer, and the frame buffer will do an auto increment, so that the next byte that you write goes to the next address automatically. And the RAM speed is at a pace that basically you can hold up a transfer of 4 megabits per second. That means half a megabyte per second. So if you calculate that, that means that a complete frame can be sent to this chip in almost 1 microseconds. And that's being said, you can send either commands or data, and with data I mean frame buffer data. So that's about let's say the highlights of the chip. We can quickly discuss the pins. So you have the pin that's called SDIN. Basically, that is the SPI data line. You have S clock, that's the SPI clock line. This is the pin that specifies whether you send a data or a command. You have the chip enable, or chip select, slave select signal, low active, and you have the reset pin, and that's it from the microcontroller perspective. Okay, let's look into the frame buffer more closely. The frame buffer is structured in 48 columns and 5 rows, as you can see in the picture. In the data sheet, they are called X addresses and Y addresses, and each byte in the frame buffer is structured with a least significant bit and a most significant bit, and the least significant bit is rendered as the top pixel in the row, and the most significant bit is rendered as the bottom pixel in the byte. The frame buffer also has a let's say pointer that is formed with a combination of the X address and the Y address, and in this way you can, let's say, manipulate the address at which the data lands. In the current example, you see that this pointer is at this location. That means X address is 0 and Y address is 0. And suppose that we write 6 bytes to the buffer, then consecutive, then they will land in these positions. And this is because we have this auto increment function. So after writing the first byte, the X address is increased automatically, and that continues until we have written 6 byte, and then the pointer will be at the 7th location. This pointer also has a auto wrap function, and that means if I'm at the X address 83 and Y address 0, and I will write exactly 1 byte, it will land on this address, and then the Y address is increased, so we will be at Y address 1, and the X address wraps, and we will be at X 0, so we will be in the second row. And this way of addressing is called horizontal mode, because we write from left to right. You also have a vertical mode, where you would write from top to bottom, but I will not further discuss that. Because of the let's say 8 bits that are in a specific row, it really lands for fonts that are 8-bit high. An example would be a 6 by 8 font, so with 8 bits high, and the width would be 6 bit. And to give you an example how that works, I have a sequence of 6 bytes that make up this 6 by 8 fonts. Actively, you use only 5 by 6 pixels, and that is because you have you want to separate vertically and horizontal the characters in display. In this case we have a bottom part of the character that is clear, and we have the left side of the character is clear. So let's see how these values map on the LCD display. So the first byte is 0. You see that as the first column here. Since no bit is on in this byte, also all pixels are off. Then if you look at hex code 23, then let's say the most significant nibble is a 2. And if you look at the most significant nibble in the second column, you see that bit number 2 is on. Then we have the least significant nibble, that's a 3. And there you see that bit 2 and 1 are on. That means 2 plus 1 is 3. And that means that the top 2 pixels are on. And that also goes for the rest of the characters. And then in the end, you end up with the percentage sign. This is a small code snippet from the library code. So if you want to make your own characters, you can do that also. But I think in the example, the ASCII characters are at least present. Now let's continue with the commands that are supported by the display. In this table, everything apart from this row are commands, and that is because here and the pin that specifies whether you have a command or whether you have data is 0. So this would be data, and the rest in the table is commands. The chip has 2 command sets called the basic command set and the extended command set, and you can specify whether you have a basic or extended command set by having another command that is called function set, and in function set you can specify power down control, but you can also say, okay, well, I want to have a basic or a extended instruction set. So first let's look into the basic instruction set. It is really simple. It is a command to set the Y address, and it's a command to set the X address. So you can calculate the addresses. They are encoded for the Y addresses in the least significant 3 bits, and for the X address they are encoded in the least significant 7 bits. That's it. And everything that is outside of this range for the Y range and that range for the X range is not valid. So with these 2 commands you can specify the pointer in the frame buffer RAM, and then you have another simple instruction that's called display control, and that specifies whether you have normal mode or inverse mode, and you have the option to disable all pixels or enable all pixels. That's it. That's the whole basic instruction set. And then you have the extended instruction set, and that is instruction set to set up more, let's say, advanced parameters of the chip. And for that I refer to the data sheet. But one thing that you can, for instance, set is the operation LCD operation voltage, VOP, that specifies the contrast But these settings are mainly used for the initialization of the chip, and you don't use them afterwards. Normally in software you also would use these addresses, but because of the simple way that I will explain in the next section, we also do not use the setting of the X and the Y address. Looking at the software, the example library is really very simple. You can write a string to a line of the display with the 6x8 font as shown earlier, and you can access the frame buffer. The whole concept is very simple. The CPU manipulates a local frame buffer on the microcontroller and sets up a DMA transfer to the display. So the main program calls a library function, and that library function does the actual local frame buffer manipulation. The advantage of this is that it is very fast and it can also be interrupted. For instance, if you get an external interrupt, you just interrupt the memory location, handle the interrupt, and you continue. And then the main program has the ability to call a library function that does the transfer of the local frame buffer to the LCD. There the CPU only has to set up the DMA transfer. At the moment the DMA transfer is started, the CPU remains available and the hardware does the actual transfer in the background. And that in itself already goes very fast. So as we saw earlier, the whole frame buffer can be transmitted in 1 millisecond. The main program also has a possibility to synchronize to see whether the transfer is finished, and that can be done by polling or callback. So that's it from a software perspective.
Now let's make a project from the start. Okay, let's create a new STM32 project. It's starting up the target selector. Let's take a chip. Take this one. Next. Project name. Well, I think LCD demo would be a nice name. Finish. Okay, let's also start up the Cube IDE. This takes a moment. Yep, I think it's there. Oh, still a moment. Yep, there it is. Yep. Okay, now let's first start with the clocks. RCC. Yeah, this board has a very special temperature compensated crystal. Let's take that one. And there's a standard low frequency crystal clock. Okay, so this is the clock setup. Then we also need to be able to communicate with the board via the debugger. So let's set up debug. Simple serial wire debugging. Okay, it's also fine. Now let's further configure the clock. So we have this 32 megahertz high-speed clock. This is the low-speed crystal. That's already okay. Then we want to have the maximum clock speed for this system that normally goes via the PLL. So I select here the high-speed clock as the input for the PLL, and that's fine. And then for the system clock, I take the PLL output. Okay, that's okay. Now I can type in 48 and then CubeIDE will do its magic and find a solution. Yeah, there it is, 48. So it sets up the PLL with the correct settings, and all the other buses are also 48 megahertz. So that seems fine. This is the maximum that is possible with this specific chip. Okay, so now we have the clock system and the debug ready. Okay, now we can add the SPI. That's under connectivity. Let's take SPI2, but before I do that, I will use a specific SPI pin, not a standard pin. That has to do with the wiring to the display of my board. It was easier to use PA10, so let's find PA10. Where is it? There is it. There it is. Let's okay. And there we have SPI2 MOSI, so we take that function of that pin. It is yellow because it's not assigned yet to a provisioned peripheral. Okay, now further go to SPI2. We want to enable it as being a transmit only master. We do not use hardware slave select, so that is being disabled. That's good. Now let's look at the GPIO settings. So it uses PA10. That's good. We just selected that as the MOSI, and what is it, PB13 as the clock, so that's also fine. Let's give it the higher I/O speed. Let's go to GPIO. No, it's not yet possible. Oh, that's for the debug. It's for the SPI. Yeah. So the maximum output speed should be very high. Okay, now the output speed is very high. Let's go back to the SPI setup. Okay, so the pins are set up now. Now go to the parameters. We have Motorola format being the most significant bit first. We want a data size of 8 bits. The prescaler baud rate is 2. Okay, we have a 48 megahertz, so if you divide by 2, that gets 24 megabits per second, but that is too high because the board can only, or the chip can only support 4 megabits divided by 16. Then we get 3, but divided by 8, it would be 6. So with this initial clock speed setting, I can only get 3 megabits, but let's take that. As also explained, the clock polarity was 0 or low. That means the clock starts off with low. The clock phase is clocking it in and the first edge. That's also good. That's fine. And then this is the chip select pulse mode. I'm not going to explain it here, but we don't need that, so it's also disabled. I think these settings are correct now. Then we want, of course, support DMA. So we add a DMA transmit channel. You see that the address increments on the memory side of things. So that's also fine. This is all okay. Then with respect to interrupts, we want to also support the interrupts. So enable those two. And then I think we are done as far as the SPI2 setup goes. Yep, okay. And now we have still some supporting things to do. So we also need a chip select or slave select signal. I have that on PB9, so let's find PB9. There PB9 is. I want to configure that, of course, as a output. Let's start off with a high signal. It's push-pull, that's okay. No pull-ups or pull-downs, they are not required. Speed, let's make it high. And also let's create a user label, because that comes in handy with software. Chip enable. Okay, that is the chip enable. Then we need a reset signal. I have that on PB10. So let's find where PB10 is. PB10. It's there. Okay. I want to also configure that as a output. Let's also start off high. Push pull. No pull up, no pull down. Make the speed high and also provide it with a user label. Reset. PCD reset. Okay. And now we still have one signal left. And that is the what is the data or command line that is specific for this chip, and I've connected that under PB14. So PB14, let's find that. Okay, here is PB14. Configure it as a output. Start with high, push pull. Let's make the output speed also high and give it a nice user label for in the software. Okay, so this should be it. Let's save the project on the CubeMX file and generate code. Yes. Yes, generate code. It's taking some while. So now we're good to add the source code. So we have a empty project with just code that was created based on the CubeMX settings. Let's create a directory under drivers to put in the library code. Let's make a new folder name. Let's give it a nice name. PCD8544. Finish. Now it's there. Okay, now let's pull in some code. I have a GitHub repository. Let's get the code from there. So this is the GitHub repository. I have just one C file and one header file. Let's directly download it. Okay. And also download the header file. Now, if I update the directory, then there they should be. Okay, these are the files just from the GitHub repository that were downloaded. There's one thing left to do. You have to be able to find and include it. So add and remove include paths. Okay, that's also fine. So now we should be good to go and should be able to compile it. Let's have a try. Build the complete project. Yeah, that seems to work. Okay. Okay, now we can try to write some application code. Oh, there's one thing that I have to explain first. That is how you port the library. So let's have a quick look at that. So in the header file of the library, you have a number of macros and that you can set with your own names of the pins. So I had my own names, PCD underscore RST. So these are the pin names we've just annotated. You have to do that also for your specific board and pin selection, but it is very easy. You just assign the correct pin name to the pins that are used by the library software. And the last thing is that you have to add what SPI resource you have allocated, and in our case it was SPI2. So here you fill in the SPI resource, and basically that's the whole thing you have to do with respect to porting. Okay, let's now continue to write a very small program. First, we need, of course, to include the library and some standard stuff to be able to handle strings. I put that in the private includes part here between begin and end, and I do this because Otherwise, in regenerating the project, it might get lost, and now it's maintained at that location. This about the header files. Okay, now we want to show a nice bitmap. So I've constructed a nice bitmap for the LCD display. Let's put that also in the right place. User code begin private variables and private variables. Let's put it here. So this is a nice bitmap. And then we go to the code in main. Also that is very simple. Let's find the proper place to have it. Here's user code after main, but before the endless loop. So here would be a nice place to put the code. Basically, it's just 3 calls. The first call is to initialize the library. The second call is to copy the bitmap that is allocated in the flash because it's constant, and copy that to the local frame buffer. And the address of the frame buffer is given by LCD get frame buffer. And of course, we use the frame buffer size. And after we've done that, the only thing we have to do is LCD write frame buffer, and then the whole frame buffer is transferred under DMA by the hardware. The software only initiates the transfer, and that's it. Let's save this, and let's try to build the whole project. Yeah, all that seems to work. That's good, very good. Okay, now we can do some testing and some analyzing on what is going on. Now let's first run debug so that it downloads to the board. The first time you have to set up the debugger. Okay. So it has been compiled and it is waiting for debugger connection. So the whole debugger is starting up now. And we stop at the first address. What I'll do now is I'll jump a little bit through the code, and then I will start up the logic analyzer to see whether we can see the SPI transactions on the bus. So let's do that. This is the standard cube initialization. And here I go to into the LCD. So this is the user code. So let's step into that. So here I'm going to do the reset, write initial commands, clear the frame buffer, etc., etc. So I will continue from here, but I will set up the logic analyzer. So I've set up 3 signals of the SPI bus and connected to protocol analyzer SPI. I'm using Pulse View, by the way, it's open source, and that can be used with very, very cheap hardware, €10 hardware. It's set up at 24 megahertz. We have a clock speed of 3 megahertz, so that should work well. And we use, after triggering, 1 megasamples of buffer. And you see that we trigger on a falling edge of D2, and the D2 is, as you would expect, the chip select. What I have to say here is that 24 megahertz with 3 channels is on the edge what this logic analyzer can do. So sometimes if I run it, it fails and I have to restart it again. But let's see what happens now. It will run, so it stops. It continues sufficiently long. I start the code. Now let's see what happened in the logic analyzer. It triggered. Okay, so now let's look at the signals we see. Zoom in a little bit. Well, first let's verify the clock speed. Let's take one. That's 1.5 clock. Let's zoom in a little bit further. Yep, this is exactly 1 clock. Now that's nice. So it's 3 megahertz. That's exactly what we specified. So that's good. And then let's zoom out a little bit. Get rid of these. And what we see is a number of transfers. And we see basically 1, 2, 3, 4, 5, 6 bytes. And these 6 bytes are the initial setup commands of the screen. You see the 6 bytes here in the code, and they are being transferred. That sets up the display correctly. If you then look at the code, we see after setting the commands, we clear a frame buffer and we write the frame buffer. So after that, you see basically the whole transaction of writing the frame buffer consecutive. This should all be zeros. That seems also to be okay. It seems to be all zeros. So here you have the frame buffer that was cleared and sent to the display. So that's very good. So if you look at the complete transaction, how long it takes, it will take a little bit more than a millisecond because we don't have the full clock speed. Let's measure it from the chip select to chip select. And there we get, what is it, around 1.3 milliseconds. So that's all as expected. And then the last part you see is basically the transaction where you push the whole frame buffer with the picture that was allocated in the flash. So this all looks very good. Let's click the analyzer away. So it seems that this is working. You also can do hello world. Let's do that maybe afterwards. The last thing I will do is that I will quickly do a code walkthrough of the library. Let's see where the library code is. So it's here. Let's first start with the interface, the header file. So as I've been telling, you see the hardware signals and the SPI resource, and then you have a call to initialize the library. You have a call to write the frame buffer. That means that you transfer the local frame buffer to the display. You have a possibility to check whether this transaction is busy, because you don't want to have don't want to write the frame buffer while it's being transferred. But on the other hand, during the transfer itself, you can just use the CPU as you want. You want to be able to get the address of the frame buffer to fill it with your own stuff. And then I made one simple function to write a text string to a certain line of the display. You can also give it a position. And then it will write a string up till the end of the line, and then it will stop. And if the string ends before the line end, it also stops. So that's it. So that is the basic interface. Very simple, I would say. Let's go to the implementation. That's not much different or not much more complicated. Here you see a large declaration of the font. It's a simple 6x8 font. It's already been explained. So the percentage sign was given in the example. Not sure where it is right now. See, oh, here it is. So exactly this one we have had a closer look at. But here we have the whole set, simple set. We have a static, so module local variable with frame buffer and a variable that indicates whether the SPI is transferring. We have a simple write commands. So what happens here is that we set the pin that specifies whether it's data or command. It has to be reset because it's when the signal is low, the command is active, and also you have to set up the SPI transaction by deasserting the chip enable pin. Here is where the magic begins. So here you use the HAL call, HAL SPI transmit DMA, and you have the buffer with the data and the number of commands that you want to send. And we have set the SPI transferring variable to 1, and then we get an interrupt. I'll go to the interrupts now. Here's the interrupt handler, interrupt callback. And what we do here is we clear the chip enable, and we indicate that the SPI is not transferring anymore. The chip of the data or command select, we just leave it what it is. If we go to sending data, we will give it the appropriate state at that moment. It's not very important what the actual state is when you're not transferring. Okay, so that's the write commands. Then we have a simple call to get the address of the frame buffer. We have the call to write the frame buffer. It's very similar to write commands. Only here you set the pin of the data command, and that means that it is data this time and not a command. Then we have the test whether to see if the transfer is busy. It's also very simple. And the last call is, oh no, that's not the last call, it's almost the last call. That is writing a line. And typically what you do is you copy a specific character that you have that is part of the string. You copy that to the local frame buffer. But if you are, let's say, that is within the last position. The last position, the character position on the screen is 14. Or you end when the string is 0. So that's also very simple call. Well, now a bit about initializing the LCD. We already saw a little bit of the code. This is, let's say, the command string to start with. I've made a little bit of a description what it does. It selects the extended instruction set, makes a chip active, and it goes for horizontal addressing. Then you set up the contrast, and then you go back to the basic instruction set, go to normal mode and set the X count and the Y count on 0, and that's all you need for initialization. You do a reset, so you toggle the reset pins, and you write the commands. After writing the commands, you already start clearing the frame buffer. Then you wait until the commands are transferred. Then you write the cleared frame buffer, so that basically clears the screen. And then you wait also for the screen being cleared. So that means that after the init, you are sure that the transfer has finished, so that the user code can decide on its own frame buffer update. And that's basically the whole code. So it's super simple code and also super fast, and I think very easy to extend with more things like drawing circles, drawing pixels, and that kind of stuff. So there's one thing left, and that is to show what is on the display.
So you might be wondering what's on the display. On display is bang, it works. I hope you liked this video, and if you do so, please give me a thumbs up, and see you next time.